about quantum lower bounds. As you may know, Andres Ambayanis was originally scheduled to give this talk, but is stuck in Latvia, so you have the Andres substitute instead. Okay, so many of the deepest discoveries of science are limitations. Things you can't do, send signals superluminally, have a perpetual motion machine, have a complete axiomatization for arithmetic, and so on. So it's a natural question. What limitations on computing are imposed by the laws of physics? And to me, much of the significance of quantum computing is that it lets us seriously address this question. And I think that's why everyone should care about quantum computing, even if useful quantum computers are never built. Okay, so let's say we wanted to investigate the limitations of quantum computing. Where could we start? Well, an initial conjecture might be, for example, that sure, quantum computers can factor, but they can't do NP-complete problems. Okay? All right, so let's try to prove that. Well, then we quickly run into a difficulty, which is that we don't even know if classical ones can solve NP-complete problems. Okay? So we're not going to resolve this conjecture. All right, so let's come up with a modified conjecture. That, well, at least quantum computers can't solve NP-complete problems in polynomial time unless classical ones can also. Well, that's still too hard. Okay. In fact, it may eventually be proven that, say, if quantum computers can solve NP-complete problems, then the polynomial hierarchy collapses. You know, if you don't know what that is, don't worry. You're not missing much. But we don't seem to know enough even about this class BQP to even make a statement like that. Okay, so let's weaken our conjecture even further. Okay, quantum computers can't solve NP-complete problems using only brute force. So if they were able to solve NP-complete problems, they would have to exploit the structure of the problem in some sort of non-trivial way. All right, well, this sounds a little bit better, but can we formalize the notion of brute force? Okay, so what is the black box model? Let's say we're trying to solve an NP-complete problem, satisfiability. So we have a Boolean formula, phi, and we want to know whether it has a satisfying assignment. Okay, now brute force might mean in this context that we restrict ourselves to only ask a restricted set of questions. So for example, does assignment X satisfy phi? No? Well, does Y? Does Z? Right? So we're not looking at the internal structure of this formula at, trying to satisfy more and more individual clauses or something. We're just saying, does this satisfy the whole formula? No? Oh, well, does this? And we keep going until we find some assignment that satisfies the formula. So in other words, we're treating this formula phi as a black box, not looking inside of it. Okay, now of course there are 2 to the n possible questions that we could ask, one for every possible assignment. And so then the question arises, how many of those questions must we ask in order to know whether any one of them has a yes answer? And so classically, clearly the answer will be about 2 to the n over 2 if we can ask the questions randomly, right? Well, then we'll find a yes answer with half probability if there is one, and if there isn't, then we won't find one. So, but then the natural question is, what if we can ask these questions in superposition? Is it then possible that even just purely treating this SAT formula as a black box, that we might discover whether any one question has a yes answer, using, say, order n queries or some very small number of queries. Okay, so now at least we have a question that looks attackable. Okay, so let me tell you a little more precisely what the quantum query model is. So we imagine that we have n possible yes or no questions. You can consider more general kinds of questions, but it's simpler just to talk about yes or no questions. And then I'll let x sub I, which is a bit, be the answer to question I. So we can think of having n inputs, x sub 1 to x sub n. Okay, and then in our quantum algorithm, each basis state of the algorithm will have the form I comma z, where here I is the index of the x sub I that we want to query, and z is everything else. So this is workspace. We can store auxiliary information there, and there's no limit on the size of the workspace. Okay, and then we'll say that a query does the following: that it takes each basis state I comma z, and it maps it to 1 minus 2 x sub I times I comma z. So in other words, it just flips the phase conditioned on x sub I being equal to 1. And it's not hard to show that this is equivalent, at least up to a constant factor, to whatever other model for queries you would want to think of. Like, for example, if you wanted to exclusive OR x sub I into some preset position on this basis state, that can be simulated by this model and vice versa. Okay, so now what is our algorithm? Well, it will just consist of a sequence of interleaved queries and unitaries. By a unitary, say U sub t, I just mean any sort of transformation on the algorithm part that we want to perform that does not depend on the x sub I, so that has no dependence on the input. Okay, so we do one of those unitaries. So the first one would typically be, go from the all zero state into uniform superposition, right? And then we make a query. And then we do some other thing, maybe a Fourier transform, I don't know, something that doesn't depend on the input. And then we make another query, and so on. And then at the end, we have one last unitary. Okay, and then we measure. So at the end, we measure in the standard basis. And so what we'll get out is a basis state, I comma z, and then some basis states will be accepting and some will be rejecting. So say, well, we'll output the first bit of the workspace, something like that. Okay? Now, I could say what quantum query complexity is. So let f of x be the function we're trying to compute. Here, by big X, I just mean x sub 1 to x sub n, so the collection of n bits. So for example, if we wanted to know whether any of the bits was 1, then f of x would be the OR function, right? And then we say that the algorithm computes f if for every input x, it outputs f of x with probability of at least 2/3. Where the probability is over the quantum measurement, right? So, and then we can define a complexity measure, which we call Q of f. You'll see different versions of this in the literature. So, if you've seen it, what I mean is Q sub 2 of f, or bounded error quantum query complexity. That's just the minimum number of queries that's made by any algorithm that computes f. Okay, so then there are two analogous measures which had been defined a while ago. There's R of f for a bounded error randomized query complexity, and then there's D of f for deterministic query complexity. Okay, and so what's immediate is that Q of f is at most R of f is at most D of f, because a randomized algorithm can simulate a deterministic one. A quantum algorithm can simulate a randomized one. Okay, so the question that we're concerned with is how much smaller can Q of f be than the other measures, right? And trying to prove a lower bound for some problem, saying that it can't be that much smaller. Okay, so as an example, we can talk about the search problem. As I mentioned, here the function we're trying to compute tells us is OR of x sub 1 to x sub n, which is 0 if every bit is 0, and it's 1 if any of the bits are 1. Okay, so that's an abstraction of sort of the Grover search problem of asking whether there are any marked items in a database. Right. So classically, it's clear that order n queries are required deterministically or randomized. Randomized, we can, again, succeed with 2/3 probability, say, if we make 2n over 3 queries. Okay, and then quantumly, we know that that the quantum query complexity of the OR function is O of square root of n, at most order square root of n. That's just Grover's algorithm, right? And our goal will be to show that Q of OR sub n is theta of square root of n. So in other words, that Grover's algorithm is optimal, that you can't do it in fewer queries than square root of n asymptotically. Okay, I'll never care about the constant factors. Okay, so there are 3 main lower bound methods that are known, and there are a few others. But so the first one to be developed was the hybrid method in '94 by Bennett, Bernstein, Broussard, and Vazirani, which is based on looking at how much each query can, looking at a change to the input and then how much that change can affect the state, as a result of each query. So sort of based on directly looking at what the algorithm is doing. And so they were able to prove a square root of n lower bound for search, by that method. Then came the polynomial method. Beals, Berman, Cleve, Mosca, and DeWolf in '98, and I'll talk a lot about that. And finally, we have the adversary method, which is due to Andrus and Bionis. So in this talk, we'll skip one, and we'll prove the search lower bound using the polynomial method, and again using the adversary method. Okay, so let's just give a high-level overview of the polynomial method. Okay, so we start by saying, so suppose by way of contradiction, right, that there were a quantum algorithm that computed this function f that we're interested in using few queries, or using some small number of queries, and we can say how small later. Okay, then what we want to argue is that, first of all, the existence of that algorithm implies that there must exist a low-degree polynomial that approximates the function we're interested in, and I'll be precise later about what that means. Okay, and next we want to use a procedure called symmetrization, which I'll show you, by which we can go from that low-degree multivariate polynomial, which is in all of the inputs, x sub 1 to x sub n, to a low-degree univariate polynomial. It's in one variable that furthermore has a large derivative somewhere and is bounded. Okay, and then we invoke our mathematician friend who tells us that this kind of univariate polynomial can exist. Okay, and so the quantum algorithm didn't exist. Okay, so that shouldn't be there. Okay, so we'll say that we'll say that a multivariate polynomial p approximates the function f if for every input, for every x sub 1 to x sub n, p is close to f. So I'll say there p of x minus f of x has absolute value at most a third, and you can place a further constraint that p of x should always be between from 0 to 1. In the asymptotic case, it doesn't matter because you can always just rescale it, right? If you have one. And then I'll call degree of f with that little toupee on it, is the minimum degree of a polynomial that approximates f. Okay, so we minimize overall, minimize the degree over all possible approximating polynomials. And then the main lemma that Beals et al. Proved is a lemma that links quantum query complexity to the approximate degree. And it says that for any function f, the quantum query complexity is at least half of the approximate degree. Okay, so yeah. Yeah, so degree just means that you take the highest degree monomial and then you sum up, yeah. So we're actually dealing with multilinear polynomials here. So you know, each of the variables, you know, will be of the form, you know, x sub I, which is either 0 or 1, right? So clearly x sub I squared equals x sub I. Okay, so all of our monomials will just look like, say, x sub 3 times x sub 5 times x sub 7 or something, and then the degree is just the number of monomials that are there. Okay. So okay, so let's say that we have a quantum algorithm and it makes some number t of queries. Then we'll just look at some particular amplitude and look at it as a function of the input. Okay. So now initially, before we've made any queries, that amplitude is a degree 0 multilinear polynomial over the input. If you think about that, that's a vacuous statement. Okay. It has no dependence whatsoever on the input because we haven't made a query yet. Okay, so now what does a query do? Well, as I said, it replaces each amplitude. I'll call the amplitude of basis state I comma z alpha sub I comma z, and it just replaces it by, it just multiplies it by 1 minus 2 x sub I, performs that conditional phase flip. And so if we consider this amplitude as a polynomial over the inputs, then this just increases its degree by at most 1, right? Okay, and then when we perform the unitaries, well, these are just linear transformations that don't depend on the input. So this is just replacing each amplitude by a sum of the amplitudes. Okay, so clearly that's not increasing the degree, right? Okay, and then finally, at the end, we measure, and then to get the probability, we have to square the amplitudes, and so that doubles the degree. And so that's what gives us this factor of 2 over here. Okay, and one thing I ignored is if the amplitudes are complex rather than real, you can split up the real and imaginary parts and deal with it that way. So, okay, any questions about that? Okay, all right. So let me tell you what symmetrization is, and I guess you have to think about this for a bit to realize that it's not completely vacuous. So now we're given, we'll say we're given a multivariate polynomial, p of x sub 1 to x sub n, okay, which has degree d. And now I'm going to define a new function as follows, that will symmetrize that polynomial. Okay, so I'll define q of k is a function for over integers k, and what it is you just take the expectation among all strings x that have Hamming weight k of p of x. All right, so q of 3, for example, you just take the average over, 1, 1, 1, 0, 0, 0, 0, 0, and 1, 1, 1, 1, 1, 0, 1, 0, 0, 0, 0, and so on, and all strings with Hamming weight 3, right? Okay, so that's what our function is, and now the claim, this is due to Minsky and Papert, is that q of k is itself a polynomial, not in the x sub i's anymore, but in k, in the Hamming weight. Okay, and furthermore, the degree of that polynomial is at most d, at most the degree of the polynomial that we started with. Okay, which means so we're progressing from the algorithm to multivariate polynomial to a univariate polynomial, and you know, so long as the degree decreases each time, right, then we're still good. Then we still get a lower bound, because then once we lower bound the thing at the end, then, you know, all of the other things in the chain must have been greater than or equal to that, which is what we want. Okay, so the proof is very short. So just let x, as I said, be the binary string, and then let this be the Hamming weight of x. And then if we consider q of the Hamming weight of x, then that'll be equal to what I'll call p symmetrized of x. So just take any string, any n-bit string that has the same Hamming weight as x, and then just take the average of p of sigma of x for all permutation sigma over the input bits. So just keep flipping around, you know, that input every way possible, and just evaluate p on every permutation, and then just take the average of all of those. Okay, and so if you think about that, you'll see that q of k is the same as that, right? And so then, furthermore, this p sub sim of x, right? Because it's symmetrized in this way, it has to be symmetric in the monomial. So if for example x sub 1 times x sub 2 has some coefficient in front of it, right? Then x sub 5 times x sub 6 has to have the same coefficient in front of it, right? So the only thing that should matter for any given monomial is how many is what's its degree. You know, how many variables are in it, right? And so then it follows that we can just express this polynomial, you know, using, say, d plus 1 coefficients, one for the degree 0 terms, and one for the degree 1 terms, one for the degree 2 terms, and so on, and then furthermore, you can if you have, say, the sum of all possible degree 3 monomials, then that'll just be equal to the Hamming weight of x choose 3, right? And that is a degree 3 polynomial in the Hamming weight of x, because you know, it's just Hamming weight of x times, you know, Hamming weight of x minus 1 times Hamming weight of x minus 2 over 6, right? It's the degree 3 polynomial. Okay, so we're done. Okay, so now comes the crucial fact that our mathematician friend provides us with, particularly from approximation theory. This is called Markov's inequality, or one of Markov's inequalities, I guess. Okay, so let P be a now univariate polynomial, which everywhere in the interval 0, comma a, so if x is anywhere from 0 to a, then p of x must be bounded between 0 and b. Okay, so this polynomial is bounded, you know, within this. We'll think of this as a large region, but on the other hand, it's not just say a constant polynomial or a linear one with a really tiny slope, because somewhere within this interval from 0 to a, p of x has a very large magnitude derivative. Its derivative is at least c, somewhere in the interval. Okay? So then what Markov's inequality tells us is that this polynomial has to have pretty large degree. The degree of the polynomial is at least the square root of a, the length of the interval, times c, the derivative, divided by b, the height of the interval. Okay, so now we're ready to just get the square root of n lower bound. So let's think of our polynomial q of k, which we got by symmetrizing that polynomial from the quantum algorithm. Okay, so if in So let's think of Q of 0. So that's just the average of the output probability for all inputs with Hamming weight 0. Well, there's only one input with Hamming weight 0, okay? And we know what the output has to be for it. No. Okay, so in other words, the probability of accepting has to be at most 1/3. Okay, and then we can look at Q of 1. So this is just the average acceptance probability over all inputs with Hamming weight 1. Okay, and for every one of those inputs, we know that the acceptance probability has to be at least 2/3. Okay, because those are all yes inputs. Okay, so Q of 0 is at most 1/3. Q of 1 is at least 2/3. Okay, so it's not hard to see that the derivative of Q is going to have to be at least 1/3, somewhere between 0 and 1. Okay, so we've got the large derivative part. All right, and now what about the bounded part? So Q represents an acceptance probability, remember. So for any integer k from 0 to n, we must have Q of k is in the interval 0, 1, because there it represents a polynomial. It represents a probability. Now the question arises: what about non-integer k? Is it bounded there also? It turns out there's a simple lemma which is due independently to Ellich and Zeller and Rivlin and Cheney. So and this was applied in our setting by Nissan and Szegedy 94. Okay, and you can just say, well, suppose that our polynomial Q strays h away from 0, 1, meaning, suppose that somewhere it achieves a value at least 1 plus h, or at most negative h, right? Okay, well then, so it must reach that value in between two integer points, right? Like, let's say between 1 and 2. So, here it's 1 plus h. Okay, but then, at 1 it had to be at most 1, and at 2 it has to be at most 1. So, it got up to 1 plus h, and then it has to get back down, right? So that means that it has to have a pretty large derivative somewhere. In particular, its derivative has to be at least, or the magnitude of its derivative has to be at least 2h, somewhere in that interval between 1 and 2, right? Okay, so now we can just apply Markov's inequality. So the degree of our polynomial is at least the square root of, first of all, what's the length of our interval, or a in the previous slide? Well, that's just n, right? Because we're considering all k from 0 to n. And then what's the maximum derivative? Well, we know it has to be at least 1/3 because of this reasoning, because it has to compute the OR function correctly. And then furthermore, letting h be how much it strays away from being bounded between 0 and 1, it has to be at least 2h, and then the total size of or the total height of the interval, I'll say, will be 1 plus 2h. Okay, and it's easy to see that for any h greater than or equal to 0, this whole quantity is omega of square root of n. Okay, so we get a square root of n lower bound, and that does it. Questions? All right. All right, so I'll just mention a couple of other things that we can get using the polynomial method. First of all, it turns out to be the case that it matters where in the interval that large derivative occurs. So if it occurs at the very beginning or at the very end of the interval, then we only get a square root of n lower bound on the degree. But if that large derivative occurs at about the middle, or if the polynomial has a large derivative, somewhere in the middle of the range, then we actually get a better lower bound of order n. And so we can use that to show that there's no quantum algorithm that computes the parity of n bits or the majority of n bits in fewer than order n queries. And in fact, we have a complete characterization for any total symmetric Boolean function. Okay, so by symmetric, I mean that it only depends on the Hamming weight of the input. Okay, so any function of that form, we can tell you what its quantum query complexity is. Okay, upper and lower, matching upper and lower bounds, basically. Okay, so and then furthermore, we can consider, so for any total Boolean function f, by that I mean any function that's defined on all 2 to the n possible inputs. So there's no promise, placed on the input, right? So for any such function, there is at most a polynomial speedup for quantum algorithms over classical ones. In particular, the quantum query complexity must be at least the classical query complexity to the 1/6 power, the 6th root. Okay, and don't you can read the paper if you want to know where the 6 comes from. It's not that interesting. And then furthermore, if the function is monotone, meaning that changing a 0 to a 1 never changes the output from 1 to 0, then the quantum query complexity must be at least the 4th root of the deterministic query complexity. Okay, so sometimes people see these things and they wonder, well, then doesn't this violate Shor's algorithm? So the answer is no, because if you think of Shor's algorithm, that's computing the the query complexity sort of core of that algorithm is period finding, right? Computing the period of a periodic function, and the key word there is periodic. So there's a promise which is placed on the input, which is that it has to be periodic with some period. Whereas here we're talking about functions where there's no promise whatsoever placed on the input. Okay. Okay, so let's move on and talk about the adversary method of ambiguous. So this is really a completely different approach, and one that physicists probably like more because it's much more physical and less sort of mathematical in nature. So the idea is that we're going to give the algorithm not just a single input, but a superposition of inputs. Okay, and of course, if it works for any one input, then it should work for the superposition too. Okay, so then we're going to consider a bipartite quantum system. So the two parts are, one, the input part, which is just the qubits of that input state that's given to the algorithm, right? And part two is the algorithm workspace. So just the whatever work bits, and querying bits are used by our algorithm. Okay, and so initially, what can we say about these systems? Well, they're unentangled. They haven't had any contact whatsoever with each other, right, before the algorithm has made any queries to the input. Okay, and then furthermore, we can say that by the end, the algorithm part and the input part must be highly entangled. So why is that? Well, so we know that in our superposition, let's say that there are some 0 inputs and there are some 1 inputs, right? Then the algorithm with high probability has to output 0 for the 0 inputs and 1 for the 1 inputs. Okay, so that means that if you look at the complete state, then the basis states of the input, that output 0, have to be associated with basis states of the algorithm part that output 0, right? And so then from that you can show that the state, has to be quite entangled under a certain measure of entanglement, which I'll talk about later. Okay, so we have that initially the two systems are unentangled. By the end, assuming the algorithm is correct, they must be highly entangled. And then the core of the argument is to show that the entanglement can't increase by much as the result of a single query. And so the conclusion is that there must be a large number of queries. Okay? Okay, so I think this will all make more sense if we look at the specific example of the search problem. Okay, so I'm going to let y sub I be the input where the ith bit is a 1 and all the other bits are 0. And I'm going to, just for simplicity, say that the problem is to find I. Okay, so so we're guaranteed that there is a 1. And now the problem is just to find where the 1 is. Okay, and it's not hard to show that that's more or less equivalent to the standard search problem where you just want to know whether there is a 1, right? You can reduce one to the other. Okay, so what we're going to feed our algorithm as input is the uniform superposition over all of those y sub i's. Okay. And then what we're going to do in order to measure the entanglement is we're going to keep track of the density matrix row of the input part. Okay, not the algorithm part. That's an important point. Okay, we're going to look at the input part. And what can we say about it? Well, so what's the initial state of rho? Well, initially, this is just a pure state, right? And so if you recall, I guess some of the previous speakers defined the notion of a density matrix, where, you just take, if it's a pure state, then you just take the outer product of the state vector with itself. So here we just have a state vector 1 over root n, 1 over root n, and so on. You take the outer product, then you just get this matrix where every entry is 1 over n. Okay, so that's our initial density matrix. Now, what about the final matrix? Okay, well here, because of the sort of reasoning that I talked about before, turns out you can show that all of the off-diagonal entries of this matrix must be small. Or by small, I mean let's say 1 over 3n, or some constant times 1 over n, right? Where the constant will depend on with what probability our algorithm has to succeed. And so there's a formal proof that I'm skipping here that involves the Cauchy-Schwarz inequality, but just from physics intuition, right? If you have an entangled state, and if you look at the density matrix of just one part of that, one half of that state, then the off-diagonal entries of that matrix have to be small. That's basically what it means for the state to be entangled, right? Assuming that the whole state is a pure state. Okay. All right. So now let's just finish the argument. I'll let S be the sum of all of the off-diagonal entries. Okay, so it's the sum of rho sub ij for all I not equal to j. Okay, so the sum of all off-diagonal entries in this matrix rho. Okay, and so initially, what can we say? Well, S will be equal to n minus 1, right? Sorry, that should be little n, the same. So, because we're just summing, the sum of all these entries is n, and sum of the diagonal entries is 1. And then by the end, we need, say, that S is at most n over 3, right? Because I said that every one of these off-diagonal entries must have decreased by a constant factor, right? So say, for example, it's at most n over 3. So in other words, the total distance we have to travel is about n, or 2/3 n. Again, I don't care about the constant. Okay? And then what we want to argue is that a single query can decrease the sum of off-diagonal entries by at most order square root of n. Okay? And so if we show that, then it follows that the total number of queries has to be at least square root of n. Okay? So the proof proceeds by decomposing that density matrix rho into a mixture of pure states. So we'll consider each possible basis state, call it I comma z of the algorithm part, and then look at say if we were to measure and get that basis state on the algorithm part, then what's the corresponding pure state for the input part? Okay, and then we'll just look at each of those separately. So I can call the pure state corresponding to this basis state, say psi sub I comma z, and then okay, and now we look at we think of making a query, and we ask, what does the query do to this matrix? Okay, and so now recall we've restricted ourselves to talking about this one basis state, I comma z. So we know that there's only one input being queried, namely exaby, right? And so then what happens? So if you recall that there's a phase flip if exaby equals 1, and there's no phase flip if exaby equals 0. Okay, so what that means is for all of the inputs other than ysaby, so for all of the inputs where the 1 is somewhere other than exaby, right, there's no phase flip, so nothing happens. The only time a phase flip happens is for that input ysaby that has exaby equals 1. And so it follows that the only row and the only column of the density matrix that can be affected by that query are the ith row and the ith column, right? Everything else just stays the same when we query exaby, okay? Okay, and now we just have to ask, well, what's the sum of all the entries in any row or any column? And now you can just use the Cauchy-Schwarz inequality, which tells you that, you know, in fact, in any density matrix, the sum of any row or of any column can be at most square root of n, right? Assuming you have an n by n matrix. Okay, and then we'll just have a convex combination of a bunch of these. So in other words, you know, we just weight each of these by the probability. So we're just sort of taking a weighted average of a bunch of things that all sum to at most square root of n, and so the n total can also sum to at most square root of n, right? So it follows that our quantity s, the sum of the off-diagonal entries, can have decreased by at most square root of n as a result of one query, and so therefore square root of n queries are required. All right, so we've just proved that Grover's algorithm is optimal by a second method. Okay, completely different method. So now you might ask, well, but we already knew it was optimal, so you know, why bother with this new method? What does it give us, right? And the answer is it gives us better lower bounds for certain other problems than we could prove using the polynomial method. So for this particular problem, you know, I speak from experience. I tried for a long time to get this using the polynomial method, and then Andres came along. Okay, so this is depth 2 game tree search. So you have an OR of square root of n ands, each of which is over square root of n variables. Okay, so it's a 2-level tree. So in other words, you first compute the AND of the first block of square root of n bits, the AND of the second block of square root of n bits, the AND of the third block, and so on, and you get the results. There are square root of n results in total, and then you take the OR of all of those results, right? And so intuitively, that corresponds to a game between two players, right? Where, you know, say me and you, we both have square root of n possible moves. So I move first, you move second, and then the question is who has the win in this game, right? Given, you know, a table of who wins for every possible combination of moves. Okay, so what's the quantum query complexity of this problem? Well, it turns out it's not hard to apply Grover's algorithm recursively for this problem. So we just do Grover's algorithm at this top level. That takes square root of n queries, or about 4th root of n. And then we apply it at this bottom level, which also takes 4th root of n queries, although we have to repeat it some more times in order to bound the error probability. And so we get that the quantum query complexity of this problem is at most of square root of n times log of n, it turns out. But on the other hand, with the polynomial method, the best lower bound that we knew how to get for this problem was 4th root of n. Okay, because I mean, you can say, you know, if you restricted this to just an and over square root of n bits, then just by the Grover bound that we showed previously, you can get a fourth root of n lower bound, or just the OR of square root of n bits again. But it seems obvious that if you compose them, then you can't do better than square root of n, right? Than applying Grover's algorithm recursively at the two levels. But it seems obvious, but you can't, proving it is another matter, right? There could be some quantum algorithm that does something completely weird that's not like Grover's algorithm, okay? So it took the adversary method to rule out that possibility and to show that actually the quantum query complexity of this problem is theta of square root of n. So again, there's just a small gap here. But again, you can't do much better than applying Grover's algorithm recursively. Okay, so another important problem for which the adversary method gave us a better bound than we knew before is for inverting a permutation. So this is like the search problem, except now we're promised that the input is a permutation of the integers from 1 to n, right? And we can query any position and get back what integer is at that position. And the goal is to find the 1. Okay, we just want to know at which position is the 1, right? And so we have some extra structure here because we're promised that there's exactly 1, 1, and we're promised that the whole thing is a permutation. So is it conceivable that there could be a search algorithm for this particular problem which is faster than Grover's algorithm? Okay, so using the hybrid method, Bennett, Bernstein, Broussard, and Vazirani showed a cube root of n lower bound on the number of queries needed for this problem. Okay, so that didn't quite rule out that there could be something slightly better than Grover's algorithm for this problem. But using the adversary method, that was ruled out. And so now we know that Grover's algorithm is still the best you can do for this problem. Okay. All right, so I'll say just a bit about the collision problem. So this is another problem where the input we're promised is a function from integers from 1 to n to itself. So there are n integers x sub I, x sub 1 to x sub n. Each of them is an integer from 1 to n. And so what we're promised is that one of two things is the case. Either x is 1 to 1, meaning that it's a permutation of the integers from 1 to n, or x is 2 to 1, meaning that every integer occurs either twice in the sequence or not at all. And the problem is to decide which is the case using few queries to the x sub I. So classically, we can say that the randomized query complexity of this problem is of order square root of n, right? Because if the function is 2 to 1, then you can work out that after you've picked order square root of n random integers, then with high probability you'll find two that are the same, in which case you know that the function can't be 1 to 1, right? Okay, and that's related to the birthday paradox, where if there are 23 people in the same room, there's a 50% chance that two have the same birthday, right? 23 being order of square root of 365, right? So, okay, so it turns out that we have an upper bound, a quantum upper bound for this problem that's slightly better, which is order cube root of n, due to Broussard, Hoyer, and Tapp. So the algorithm is very simple. You just look at cube root of n integers, just query them classically, and then you can imagine that you sort them for fast lookup. Then you go into an equal superposition over n to the 2/3 other x sub i's, and then for each one, you ask the question, is this equal to any of the pink x sub i's, the ones that were queried classically? And if it is, you count it as a marked item, and if it's not, you don't. And then you just perform Grover search on these n to the 2/3 items, right? So Grover's algorithm will take square root of n to the 2/3 time, which is n to the 1/3 time, Okay, so this part takes cube root of n time. This part takes cube root of n time. So the total time used is cube root of n. And furthermore, the total number of comparisons of entries is n to the 2/3 times n to the 1/3, or n. Okay, so again, for the same reason as in the classical case, if the function is 2 to 1, then there will be a marked item here with high probability. So that you will find a collision with high probability. Okay. So now the question is, can we do any better than this in the quantum case? And so for a while there was no lower bound. There was no non-trivial lower bound known whatsoever, not even, say, log of n, right? We only had the sort of trivial constant lower bound. So then the result that I'll show is, well, actually, I won't show it. I'll just summarize it, is a lower bound of n to the 1/5, okay, that any quantum algorithm for this problem has to use at least n to the 1/5 queries, and subsequently Yaoyan Shi improved my result to show that you need n to the 1/4 queries. And then furthermore, so I defined this problem as having where the integers have a range from 1 to n, but if you allow the integers to have a larger range, in particular like at least 3/2 n, then you can actually get a tight lower bound, one that matches the upper bound, which is you need at least cube root of n queries. Okay? And so why is this lower bound so much harder than the search lower bound? Well, the basic reason is that if you think of a 1-to-1 function and a 2-to-1 function, right, they're very, very far apart from each other. In fact, they have to differ in at least n over 2 places, right? And so, so any argument that relies on, say a yes instance and a no instance being very close to each other, will necessarily fail, right? So, there are arguments that are based on so-called block sensitivity, which basically means that if you have a no input, then you can change it in a lot of separate or disjoint places in order to make it a yes input. Okay, but for the collision problem, that's not the case. If you have a 1-to-1 function, then there are at most 2 disjoint ways that you can change it in order to make it a 2-to-1 function. Okay, so something different is going to be needed. And so as for motivation for this problem, I think Leonard mentioned in his talk that this is a very abstract model for, say, the non-abelian hidden subgroup problem, right? If this is saying if you don't consider the group structure of your problem at all, then could there be some completely trivial brute force type of quantum algorithm for graph isomorphism and for problems like that? And so this says that the answer is no. Okay, so cartoon version of proof. All right, so first of all, we're going to imagine feeding the algorithm g-to-1 functions, where g is an integer that could be greater than 2. So even though the problem is to distinguish 1-to-1 from 2-to-1 functions, we'll imagine what happens if we give the algorithm 3-to-1 or 4-to-1 functions and so on. Okay, and then I'm going to define P of g to be the expected probability that the algorithm outputs 2-to-1 when the input is a g-to-1 function chosen uniformly at random, right? So P of 1 has to be at most 1/3. P of 2 has to be at least 2/3, but then P of 3 and P of 4, P of 5, and so on could be anything, right? Because there we're giving the algorithm an input that violates the promise. But on the other hand, for every g, even the ones greater than 2, P of g has to be from 0 to 1. It has to be bounded. Why? Well, just because of the probability. Probabilities are from 0 to 1. Okay. And then we said that P goes from at most 1/3 to at least 2/3 as g goes from 1 to 2. So it has a large derivative somewhere. Okay. Oh, I skipped the crucial part of it, which is that this function P of g actually turns out to be a polynomial. Okay, so it's a polynomial in G. So we started with a polynomial, over the inputs, over the x sub 1 to x sub n, and it turns out that we can actually symmetrize to get a polynomial in that parameter g. So I won't prove that. Furthermore, the degree of that polynomial p is, as before, as for the search case, it's at most twice the number of queries that are made by the algorithm. Okay, so so now we have this polynomial, okay, and it's bounded, and it has in this fairly large region, and it has a large derivative somewhere in that region. So we can use Markov's inequality to get a lower bound on the degree of that polynomial, therefore on the number of queries that had to have been made. There's an important caveat here, which is, what does the g to 1 function even mean if g doesn't divide n, right? And you can see how it could get ugly. You have like a 3 to 1 function on 7 inputs or something. And so, incidentally, this is related to why the argument I've sketched breaks down for when g is greater than the square root of n, because then a g to 1 function versus a g plus 1 to 1 function, right, are almost indistinguishable from each other. So, okay, any questions about that? All right. All right. So I'm going to give you my own sort of idiosyncratic list of 4 open problems about quantum lower bounds that I think are kind of nice. Okay? Okay. So first of all, let's look at the collision problem again, and let's suppose that our input is 1 to 1 rather than 2 to 1. And I'll imagine here now that the input is exponentially large, right? So we give it an n-bit string as input, we got another n-bit string as output. Okay. So now the question is there a succinct quantum certificate that proves that input is 1 to 1 rather than 2 to 1, right? If it's 2 to 1, then it's clear that there's a certificate. I just tell you 2 indices, where x sub I equals x sub j, and that proves it's 2 to 1. Okay, but if it's 1 to 1, how would I prove that to you? Okay, so let's say to be as general as possible, let's say I can give you. Have you give me, all right. So you say you can give me a quantum state, a quantum state with polynomially many qubits, and then I can use that, to perform, using that state, perform a polynomial number of queries on the input. And then can I then verify that you're not lying and that the function is indeed 1 to 1 rather than 2 to 1? Okay, second problem. So we know, as I said, that there's at most a 6th power gap between quantum and deterministic query complexity for any total Boolean function, any Boolean function defined on all 2 to the n inputs. So, it follows that the same must be true for randomized classical query complexity. Okay, so my question is, can we show a similar bound if the function is not quite total but almost total? So if it's defined on, say, a 1 minus epsilon fraction of inputs. So there's only a very, very weak promise on the input. Okay, and the reason I'm interested in this question is if you get it, it would be a large step towards the following conjecture, which, well, I conjecture, okay, that suppose BPP is not equal to BQP relative to a random oracle with probability 1, okay, then BPP is not equal to BQP. So you're not going to separate those 2 classes relative to a random oracle without separating them, period. Okay, so if you don't know what a random oracle is, don't worry. Okay, again. So, all right, so my third question. So let's say we change the oracle model just a little bit, and we say that whenever our quantum algorithm makes a query, replacing I by I tensor x sub I, then that answer register, the x sub I register, has to be measured immediately. Okay, so not the I part, but just the exabyte part is measured right away. Okay, now if you think about it, that's exactly what happens in Shor's algorithm, right? We have this uniform superposition, then we compute x to the r mod n, and then we say, now you might as well measure that second register, right? You don't have to, but it doesn't matter if you do. Okay, so clearly we can still do Shor's algorithm in this sort of or period finding in this sort of oracle model. But on the other hand, you can show that we can't do Grover's algorithm in this model. To do Grover's algorithm, you need to be able to make a query and then do a phase flip conditioned on that query and then uncompute the query, right? And you can't uncompute exabyte if you've already measured it. Okay, so my question is now, is there any total Boolean function for which you can get any asymptotic speed up over the classical query complexity in this oracle model? I conjecture that the answer is no. And I put the stamp of physical motivatedness on this question because David DiVincenzo has told me about there are possible quantum computer designs, and I may just be making this up, but okay, there are two kinds of spins. There's like nuclear spins and electron spins, and one of them, say the electron spins, is very easy to initialize into the all-zero state, but has a very short coherence time. And the other one, say the nuclear spins, pretty sure it is the nuclear spins, is very hard to initialize into the all-zero state. So it's in something like a maximally mixed state, but it has a very long coherence time. So you can imagine that the I register has electron spins and the exabyte register has nuclear spins. No, that's the right way. No, because you mean the nuclear spins have the short coherence time? Yeah, no, then that's right. Then you want the ones with the long coherence time to be in the second register, because there it doesn't matter if you initialize it to the all-zero state or not, right? It's okay for this to be in a maximally mixed state because you're going to measure it right away anyway. Okay. So. All right, so this oracle model, corresponds to that sort of quantum computer design. All right, so my fourth question, this is one I just made up recently. Let's say that the inputs to Grover's algorithm are arranged somehow in space, right? So we're trying to search an actual physical database, and our inputs are arranged on a square root of n by square root of n grid. Okay, and there's a marked item that we want to find. And our quantum computer, we'll say, has unlimited memory. So, once it's seen some square on this grid, it never needs to go back to the same square, right? But on the other hand, the speed of light is finite, as it is in reality. So, to move this read head, or to move our quantum computer one square takes unit time. Okay, so, but it's a quantum computer, so we can go into superposition. That happy face is the quantum computer. Okay, so now my question is, can we do search in anything less, can we do search any faster than classical in less than order n time, right? Because we could do it classically in n time by just going through all the squares, or we could do Grover's algorithm, but if we do Grover's algorithm, there are square root of n queries, and each one takes square root of n time, because it takes square root of n time, just to get to the marked item. Okay, so I conjecture that that's actually a lower bound, but, I have to show that. Okay, so that's it. Thanks.